Hi everyone. So this is the last time you'll have to listen to me do a recorded lecture. Woohoo! I hope that these have been helpful to you. This topic is going to be on problem solving. Um, so it's actually not a lot of material, and hopefully I can buzz through it pretty quick so that this is painless for you guys as you're sitting there listening to it, and hopefully learning the information for the rest of the course. And then you're all done, and you just have to take your exam. So that's pretty exciting. Um, so, as far as problem solving is concerned, obviously, different people solve problems differently. We put a lot of different things into solving a problem. It really depends on things like our personalities, the way we think through things, our personal experiences. Um, just in general, the the way that we've gone through our life is going to help us solve our problems. We find that as people age, they become better problem solvers because of personal experience, because of memory, and things like that you guys have discussed throughout the course of the semester. Um, and we also know that there are different types of problem solvers. So, there are some people that solve problems more creatively. There are some people that solve problems at a basic level because they just don't have the information. And then there are people who solve problems as experts, expert problem solvers. Um, so, really, it depends on the person. So, today we're going to talk about how we solve problems, um, problem solving as a search, problem solving heuristics, and problem solving by analogy. So, what is solving a problem? Obviously, so problem solving is figuring out how to reach your goal, how to get from point A to point B. Um, obviously, this is something we do all the time, like trying to figure out how to get places when we don't have appropriate transportation, or how to get all of our work done by the end of the semester when we only have a week left, or, apparently trying to get a cat to stop jumping on the counter, or opening the trash can, or stealing the feather duster. I'm assuming these are things that Dr. Starling has experienced. I don't have a cat, so I don't know. Um, I have problems that I try to figure out, like, how do I stop my 3-year-old from licking the window? Yes, that happens. So, you know, and then I guess we have a more serious problem at the bottom here. How do I prove this theorem from these premises? Um, so, what all of these different things share is that in each case, the person has a goal and they're trying to figure out how to get to that goal. And that defines problem solving. So I'm going to give you guys a common logic problem you may have heard before. Farmer Tim needs to get a wolf, a goat, and a cabbage across a river. Why Father Tim needs to do this? Or farmer, not father. Sorry, too much details in my brain. I just resorted to father instead of farmer. Farmer Tim needs to get a wolf, a goat, and a cabbage across a river, which is just kind of a strange situation to me, but okay, Farmer Tim. His boat can only hold himself and one other thing. If he leaves the wolf and the goat alone together, the wolf will eat the goat. If he leaves the goat and the cabbage alone together, the goat will eat the cabbage. How can he get three things across the river without having something get eaten? Um, so if you want to take a few minutes and try to figure out how to solve this problem, I'm going to put a discussion board up for this, and you guys can go ahead and write the answer in the discussion board. Once again, this stuff goes towards your class participation. I know you also have zaps that look very similar to this problem. There's the missionaries and cannibals zap, which is pretty much the same type of question. And I'll be looking at the data for those later. So generally, a lot of researchers look at problem solvers as a process of search. Like you're navigating through a maze or trying to get from point A to point B um, on a map or something like that. You're trying to find the path to make your goal. Um, so you obviously have various moves that you can make throughout this. And you have your initial state, which is your starting point, and your goal state, which is your desired endpoint. And then you have your operators, which are the tools and actions you can use to change your current state. So what can you do to get yourself from point A to point B? And then lastly, you have your path constraints. So these are the things that block your path, the things that limit you from taking certain options. So there are some issues problem solving as a search because what we call the problem space, so all the states that can be reached in solving a problem, can be often too big. And that makes it really hard to solve the problem quickly and efficiently. Um, so this is an example of chess. You know, there's all these different options when you're making moves in chess to solve a problem. So and win the game. So obviously, if you try to use problem solving as a search and you don't have any strategies or heuristics, this can make things very, very hard. And that's why people who play chess regularly, they actually use problem solving heuristics, which I'm going to talk about in a minute, to help make there be less of a problem space. I know that Dr. Starling in these slides talks later about this problem, but I'm going to mention it now, and then I'll kind of just go through it quickly later. So there's 5 orcs and 5 hobbits on the east bank of the muddy river. They need to cross to the west bank and have located a boat. In each crossing, at least one creature must be in the boat, but no more than 3 creatures will fit in the boat. And of course, if the orcs ever outnumber the hobbits in any location, they will eat the hobbits. Therefore, in designing the crossing, we must make certain that the hobbits are never outnumbered either on the east bank of the river or the west. How can the creatures get across without the hobbits being eaten? So, this is a problem that's used in a lot of different studies. It's very similar to the cabbage and the goat and the wolf. And if you were going to use problem solving as search to figure this problem out, you would have to trace or trace through the entire problem space. You would have to explore every branch. So that would be like similar to exploring every single branch or every single turn in a maze, every single corridor, every single dead end. So you'd have to figure out every approach you could possibly take. This can be incredibly time consuming um, to narrow things down. So sometimes our problem space is just too big. We can't possibly consider every option. Maybe with the hobbits and orcs that would be a little bit easier, but like with the chess game, that would be almost impossible. So then we have to figure out the best one. We have to figure out the best option, but we can't use problem solving as a search. So how do we do that? We use heuristics. So you guys remember listening about the availability heuristic and the representativeness heuristic. So we're going to talk a little bit about how heuristics work in problem solving. They help us narrow the search space, and they still will hopefully lead us to a solution. So in order to figure out how problem solving heuristics work, people use problem solving protocols. They ask people to tell us what they're doing as they solve a problem. And we use this to identify the strategies being used. So now we're going to talk a little bit about the different problem solving heuristics. The 4 are hill climbing, means end analysis, working backwards, and mental models and images. So as far as hill climbing is concerned, you have to think of the goal as being the top of the mountain, and to reach that goal, you need to go up. While you're going up, you're going to hit forks in the road, and you have to pick the one that's going to get you to go up. Um, so this problem solving approach works the same as it would as if you were climbing a hill. Your ultimate goal is to get to the top. So at each point in problem solving using the hill climbing strategy, you're going to choose the option that moves you in the direction of your goal. While this can be helpful, it's often limited use because a lot of problems require that you have to move away from your goal. And then when you're in the new position, you can see a better solution or how to move closer to your goal. So, you know, for example, the idea of absence makes the heart grow fonder. If you're trying to get somebody to pay attention to you, um, if you're around all the time, they're not going to notice maybe the things that they notice about you. But if you go away for a while, they might notice something that makes you memorable. I just almost used a word that my 5-year-old son used. Instead of saying memories, he says rememberies, and I almost said rememberable. But you know, so in order to get from point A to point B in that situation where you're trying to get somebody to remember you, you're going to move away for a while maybe, and then come back. So hill climbing can be a useful heuristic. It's easy, it guides us along a promising path, but it doesn't always work because sometimes we have to move backward in order to go forward. The good thing is that we have other heuristics available to us. So another one is the means end analysis. So you start by comparing state to your goal, your current state to your goal state, and try to figure out what you have to do to make your current state more equal to your goal state. This helps us identify what we need to do next. This is the example that's used in the book. So I want to take my son to nursery school. What's the difference between what I have and what I want? One of distance. What changes distance? My automobile. My automobile won't work. What is needed to make it work? A new battery. What has new batteries? An auto repair shop. I want the repair shop to put in a new battery, but the shop doesn't know I need one. What is the difficulty? One of communication. What allows communication? A telephone. Um, I actually really don't like this example so much. I just saw it in the text and I was like, oh, let me use this as an example. Um, but using that problem that I just said, you have to figure out like what you have to do to make your current state work a little bit better, and be more close to the end state that you would like. So a better solution or a better problem to point out is probably breaking a problem into smaller subproblems, like baking cupcakes. You know that you have a lot of different things you have to do, steps you have to take to bake cupcakes efficiently. So you look at your current state, which is having no cupcakes, and figure out how to get to your end state, which is baking cupcakes. I'm actually going to. I have a really good way to look at means end analysis. I'm going to see if I can find it for you guys and post it. So you can look at the link for it later. It's all about how to make a sandwich. When you want a sandwich and you don't have a sandwich, what do you do? And this is a good way to remember this. So I'll post it on Blackboard, and it's funny, and you should look at it. So working backwards is almost exactly the same as means end analysis. We're just doing things in reverse, and we are trying to look at how we got to where we are, and or what we have to do to get to where we are from the goal state, and going back and looking at the initial state. This is useful for certain problems. And here's an example of a problem that uses working backwards. Water lilies on a certain lake double in area every 24 hours. From the time the first water lily appears until the lake is completely covered takes 60 days. On what day is the lake half covered? So day 1, you have 1 lily. Day 90, you have all water covered with lilies. So you have to figure out how to go backwards with this. I'm going to give you the solution after giving you a couple seconds to think about it. So, on what day is the lake half covered? The idea is that the lake is half covered on the 59th day. And the explanation for this is since the water lilies double every day, the lake is half covered the day before it is fully covered. So if you start with 1 lily, the next day it doubles till 2 lilies, then it's 4 lilies, then it's 8 lilies, and so on and so forth. So basically by using multiplication, you can go backwards and see where you will be when the lake is half covered. We also see that sometimes people use problem-solving heuristics by translating a problem into terms that lead them to create an image or a model. So this is very good for problems with spatial arrangements. So we have what we call the bookworm problem. So here's that. Oops. Hold on. Solomon is proud of his 26-volume encyclopedia, placed neatly with the volumes in alphabetical order on his bookshelf. Solomon doesn't realize, though, that there's a bookworm sitting on the front cover of the A volume. The bookworm begins chewing his way through the pages on the shortest possible path towards the back cover of the Z volume. Each volume is 3 inches thick, including pages and covers, so the entire set of volumes requires 78 inches of bookshelf. The bookworm chews through the pages and covers at a steady rate of 3/4 of an inch per month. How long will it take before the bookworm reaches the back cover of Z volume? So when given this problem, many people will try to use an algebraic solution and end up with the wrong answer. And the reason behind this is that they're calculating into their equation that the bookworm is is chewing through all of book A and all of book Z. But if you look at the picture below, when you put the covers, if you put the books the way described, if the bookworm is sitting on the front cover of the book, he will be sitting already with all of the volume contents, all of the contents of book A behind him, and he won't get to the entire pages in book Z either. So he will start with A at the cover of A, and he will chew through books B through Y, and then end up at the back cover of Z. I hope that makes sense. I had a little bit of an issue translating when I was trying to figure out how to best explain it. But when people are given the picture, they're much more likely to notice, oh, well, he doesn't have to chew through all of A, and he doesn't have to chew through all of Z. So then they get the right answer. So based on the information I just provided you on these 4 different strategies, you can think of what the advantages and limitations might be. As for example, with mental models, it might be hard for certain people to visualize a mental model, or some people are just not good using spatial reasoning to help them solve a problem. With hill climbing, there may be still too many options of ways to get up that hill. Or there might be, and it's impossible to see the top of the hill by taking a step back, as discussed. So I mentioned what some of the advantages and limitations were as I was going through, and you can kind of assume what the other ones are. So as far as strategies are concerned, so one of the best things we can do when we're trying to solve problems is using knowledge that we already have. And I've mentioned a couple times already throughout these slides that one of the best things to use for problem solving is our past experience, especially with specific problems. If there's a similar problem we've solved in the past, the knowledge that we have from a past problem might help us solve a future one. Another strategy that can be used to help solve problems is problem solving via analogy. And that's basically finding a comparison or analogy between the current problem and the one you've already solved. And you have to use what you know about the solution of the previous problem to derive the unknown solution. So you have to use what we know to discover new solutions. Here's some examples: understanding a human heart by comparing it to a pump, understanding molecules by comparing them to billiard balls. One of the more famous ones that's used is the tumor problem, which I believe Dr. Starling mentioned later in the slides, and I will go ahead and mention that in a minute. Here's that orcs problem. 5 orcs and 5 hobbits are on the west bank of a river. They need to cross the east bank to the east bank using a boat that holds at most 3 creatures. On each crossing, there must be at least 1 creature in a boat. If the orcs ever outnumber the hobbits on either bank of the river, they will eat them. How can the creatures get across without any hobbits getting eaten? So here we can use that wolf, cabbage, goat problem, the history of that, to solve this problem about the orcs and the hobbits. So using an analogy or using past experience often makes problem solving easier. So training on analogous problems can help improve problem solving, but it doesn't help you at all if you are not aware of the similarities between the past situation and the problem at hand. Not ham, because that doesn't make any sense. I got to stop recording slides at like 10 o'clock at night. It's not good for me. So in a study by Reed, Gick, and Holliak, it was found that participants were faster in solving second problems after training on an original problem. But they were only faster in solving the second problem when the relationship was explicitly pointed out to them. So when it was shown to them why that first problem could help the second problem, that was only when the analogy was helpful. And it seems that usually we don't use analogies spontaneously. Like, we're not sitting there and there's a problem that comes along and I'm sorry, I'm laughing because I thought there's a problem comes along, you must whip it. And that doesn't help at all with this slide. But anyway, when a problem comes along, we're not sitting around going, okay, what can I compare this problem to? Usually we try to find something else to compare the problem to, or just not compare the problem to. Usually we find something else to use to solve the problem, and we're not usually looking for analogies that work. So doing this spontaneously without being trained or primed to use the analogy does not seem to be something we typically do. So how do we find the right analogy since we can't really do this spontaneously? So really we need to look into the deeper structure of the problem, and we can't just look at the surface structure of the problem. We have to figure out how to place the current problem onto the earlier problem, like map it on top. But the problem here is that people are usually led astray by the surface similarity. So for example, I'm going to tell you about the tumor problem in a second, and in this case, when somebody is given this problem, suppose you are a doctor faced with a patient who has a malignant tumor in his stomach. To operate on the patient is impossible, but unless the tumor is destroyed, the patient will die. A kind of ray at a sufficiently high intensity can destroy the tumor. Unfortunately, at this intensity, the healthy tissue that the rays pass through on the way to the tumor will also be destroyed. At lower intensities, the rays are harmless to the healthy tissue, but will not affect the tumor. How can the rays be used to destroy the tumor without injuring the healthy tissue? So now, without providing you with an analogy, what would you think about here to solve the problem? You probably wouldn't be thinking, okay, what else can I compare this to? You'd be thinking, what else do I know about tumors? How are tumors typically treated? What are some ways that we could figure out how to treat this tumor using this treatment and not harm the healthy tissue? But you're not going to be thinking about anything past that surface structure. So when giving the tumor problem alone, people have a hard time solving it. So then often when studying this tumor problem, a hint is given, and this hint is called the castle problem. So here's the castle problem. A dictator ruled a country from a strong fortress, and a rebel general, hoping to liberate the country, vowed to capture the fortress. The general knew that an attack by his entire army would capture the fortress, but he also knew that the dictator had planted mines on each of the many roads leading to the fortress. The mines were set so that small groups of soldiers could pass over them safely, since the dictator needed to move his own troops to and from the fortress. However, any large force would detonate the mines, blowing them up and also destroying the neighboring villages. The general knew, therefore, that he couldn't just march his army up to one of the roads to the fortress. Instead, he devised a simple plan. He divided his army into small groups and dispatched each group to the head of a different road. When all were ready, he gave the signal, and each group marched up a different road to the fortress, with all the groups arriving at the fortress at the same time. In this way, the general captured the fortress and overthrew the dictator. So, when people were presented with that problem as well, they were much more likely to be able to solve the tumor problem. So the percentages, hold on a second. Um, The percentages were that when using the hint, 75% were able to solve the tumor problem, and without the hint, only 10% solved the problem. So 75 with the castle problem helping them with the tumor problem, and 10% when they weren't given that. So obviously, when we're provided the information to use an analogy, it's much more simple for us to solve that other problem. But without searching, without that ability to be provided with that information, or the thought that we should search for that analogy, it doesn't really help us out so much. Expert problem solvers use deep structured things to solve problems, but analogy usage tends to be domain specific. So again, we're much more likely to look at things that are involved in our domain. For example, in a study looking at physics PhD students sorting physics problems. Novices tended to place all the problems together, um, involving things like river currents, all the problems involving springs, and so on, in each case focusing on the surface form of the problem, independent of what the physical principles were needed to solve a problem. Um, in contrast, the experts ignored the details of the problems and instead sorted according to the physical principles relevant to the problem solution. So because of their expertise, the physics PhD students sorted things involving the physics, whereas those people who aren't physics experts sorted the problems based upon other principles, like just the similarities of the things that those things had. In another study by Novick and Holyoke, math SATs correlated with better math analogy usage. So, in general, experts have more cross references in their memory. They have more experience and things to look up, if you will, and can pick up associations that other people miss. So, they're much better at looking at that deeper surface, that deeper area than just the surface area. So, how can we get non expert people to use analogies? We have to draw attention to principles rather than surface features. So Gick and Holyoke in 1983, when they were looking at the fortress versus the tumor problem study, discovered that two training problems are better than one to help people use analogies. In a study by Cummins in 1992, he instructed participants in one group to analyze a series of algebra problems one by one. Participants in the second group were asked to compare the problems to one another, describing what the problems had in common. The latter instructions made the participants think about the problem's underlying or deep structure, and because of this, they were more likely later on to use those training problems as a basis for forming and using analogies than the people that were just asked to analyze the problems one by one. And in another study by Needham and Begg in 1991, participants were presented with a series of training problems. And some people were told they were going to need to recall that later, and others and were encouraged to work at memorizing them. The other group was encouraged to work on understanding each solution so they'd be able to explain it later to another person. So it's memorizing versus understanding. When the time came to test the problems, the people in the second group were much more likely to transfer what they had learned earlier. As a result, those who had taken the understand approach were able to solve 90% of the test problems. Participants who had taken the memorize approach solved only 69%. So that's a pretty big difference. So that's actually something that you guys should think about when you're working to study for finals next week. That when you're just working to memorize information for your classes, you're less likely to remember it and be able to translate it onto whatever you're doing on the test, whether it be essays or multiple choice or whatever the case may be. So when you use that rote memorization, it's really not that beneficial to you in the long term. However, if you use understanding to learn your materials, that's much more beneficial to you. And I usually say that the best thing to do is to try to um, take whatever the material is and kind of, I'm having a word finding issue here. Sorry for like the presentation stopping and starting there for a second. I was trying to remember a word that I tend to use when I'm talking about um, learning information, and I have that tip of the tongue thing that I'm sure you guys learned about in this class. And it's really frustrating. So I tried to pause for a few minutes to try to remember what word I was thinking of, and it's still stuck. And I know it begins with an E, and it's driving me crazy. So I'm just gonna say it some other way, and I'll probably remember the word at like 3 o'clock in the morning. Um, and then I'll do an addendum to our slides. Just kidding. Um, so what I usually say when you're trying to learn material, the best thing that you can do to learn the material is try to do something that gives it meaning to you, and to learn by expanding upon it. So not just sitting there and rote memorizing, but making examples, giving yourselves ways that work for you to remember it. So one of the things that I usually had to do I usually did when I was trying to remember something, was I usually remember things a lot better when I have a visual reminder. So sometimes I'll figure out ways to make a doodle that involves whatever it is I'm trying to remember, and that's my way of elaborating on it so that when I get a test or something in front of me, and yes, I still have to take tests sometimes, um, I look at it and I can think about that picture I drew and it clicks in my head. So um, that's one of the things that when you guys are ready to take finals next week, you should keep in mind for when you're studying. Is it's better to just not sit there and memorize, but to make it mean something to you. With that being said, I'm going to end these slides. There are a few things that Dr. Starling didn't cover in this section of the class, which I'm a little sad not to lecture about. I continued, I can't even speak. I considered um, making another slide presentation for you guys, but I'm sure you have enough on your plate, so I'm not going to do that to you. Um, I'm just going to leave you with one final problem that you can go ahead and try to figure out, and this is something involving functional fixedness, which is a tendency that we have rigidity to only think about an object's function and not about the other things it can do. So I don't know if you guys ever talked about this throughout the class, but I just think this is a cool problem and I like to talk about it. So I'm just going to end with that. And if you guys don't have the text, then this will be something new for you. So this is called the two-string problem. You enter a room in which two strings are hanging from the ceiling and a pair of pliers is lying on a table. Your task is to tie the two strings together. Unfortunately, though, the strings are positioned far enough apart so that you can't grab one string and hold on to it while reaching for the other. How can you tie them together? So I'm going to end with that problem. If you've read it in the book, you're going to know the answer. Um, if you haven't read it, um, you can feel free to jot it down in an email to me or whatever you want. And if not, I will see you guys next week at the final. I'll be sending out an announcement within the next day or so about the exact structure of the final and in the review sheet, like Dr. Starling has done for you guys, and we'll go from there. Please let me know if you have any questions before you hear from me again, and see you next week.